I thank the organizers for arranging this conference and giving me a scope to talk about some recent results on boundary driven processes. This is a recent work I have done and actually been doing with Pritha. She is in NIT Surathkal and this is recently put to archive. So, the model is as I just mentioned, it is a boundary driven active process, and actually we have taken the run and tumble process as an example of an active process. So, there are two paradigm of non-equilibrium, two well studied paradigm. One is this boundary driven. So, a system in which some dynamics is going on, but it is connected to particle or energy reservoirs at the two ends or at the boundaries, which drives the system out of equilibrium. And the second one is at the single particle level, the system violates the condition of equilibrium, as you have been listening, as it happens for active process. Here we are considering this run and tumble dynamics, where in one dimension, where the particle has a preferred direction of motion, and with some certain rate it can flip the preferred direction, and we consider the effect of thermal noise. So, the equation of motion will be simply this, and now a system with many non-interacting run and tumble particles, it is attached to particle reservoirs at two ends. So, the particle reservoir is also active in this case. So, it contains many non-interacting run and tumble particles, and the effect of the reservoir is just to give some fixed boundary condition. So, with this setup, so we ask some questions related to its properties in the steady state, what will be the transport properties, and what are say the long time distribution and the relaxation behavior. So, completely non-equilibrium statistical physics characterization we are looking for. So, to characterize this kind of system, usually we try to find the distribution of the particles at different times. So, here the particles come with two internal states, one is, so two states you just randomly assign one to be plus and one to be minus. In one day it can move in one direction and the other direction, so you call it P plus and P minus, and if you somehow know this vector at different times, so you have the answer. So, we are aiming for that, and for this you solve this master equation with this boundary condition, and once you evaluate this P plus P minus separately, you can calculate the total density and total magnetization. So, this is the standard protocol, and we start by asking what are the steady state properties. So, this is a boundary driven system. So, we expect that for boundary reservoirs with two different densities, there will be also be a current. So, it will also have a transport behavior. So, we ask what is the steady state and transport. So, the equations I have just shown, in the steady state the left hand side is 0 and it can be quite easily solved, and you get a solution. So, this is the current. So, in this case first we consider that the boundary reservoirs, they provide only non-zero density. Although these are active reservoirs, it is giving in active particles, still first we assume that the magnetization of the boundary is 0. We will later see that what is the effect of non-zero boundary magnetization. So, with this boundary magnetization, the current is very much like a diffusive current. It depends on the density difference of the two boundaries. There is this well known effective diffusivity, and it is divided by the length, which is slightly modified by a constant. So, for large system size it is effectively a diffusive current. So, very much like passive. So, not much of a difference apparently. If you look at the distribution and magnetization profile, this is the distribution. So, two reservoirs, they are throwing in particles and particles also getting absorbed into the reservoir. So, apparently this is not really linear profile as we usually get. But this is for a small system. If you do a large system, take a large system limit, then you find that this is actually linear in the bulk, and these non-linearities come at the boundaries. This mu, this is a something of order 1, it is a length scale, mu inverse is a length scale, and you form a boundary layer. So, in active process, boundary layer is known. For example, when the particle is moving in a reflecting within a reflecting barrier, so at the walls there is a boundary layer is formed. But here we see that even when there is this open boundary condition, a boundary layer is there, but still in the bulk it is largely diffusive, and the non-trivial, or maybe you say new effect of activity, comes in the magnetization. Magnetization is just a difference of the plus and minus kind of particles, and although at the boundaries the magnetization is 0, in the bulk we see a finite magnetization. And this happens because that in the boundaries they throw in equal number of plus and minus particles, but the two boundaries there is a difference. So, the minus kind of particles they go out rapidly, so an excess of plus remains. So, this is why although there is a 0 boundary magnetization, finite magnetization is appearing. And one interesting thing is that this excess in the length that appears in the current, the length is effectively increased by some amount, and it turns out that this is exactly equal to the Milnor length. We will see later why this is the Milnor length, but it appears in the steady state also. And so, this is one kind of summary for the steady state with this particular boundary condition. Now, if you have non-zero magnetization at the boundaries, so what will happen? So, the first thing we see that the expression of the current changes. So, there is this gradient part, the density gradient drives a current, this is there, but also another component appears in the current which is driven by the boundary magnetization. So, the picture goes like this. So, you have these two reservoirs where you have equal density of particles, but the particles have different average different spin in these two reservoirs. You can construct reservoirs quite easily, I mean at least theoretically. So, what happens at one reservoir, say and q1 plus q0 is greater than 0, assume let us say. So, from this reservoir also you push some particles into the system, and here also you pull some particles in the same direction if both are positive. So, in the middle some current is induced. Apparently this is like some kind of external drive. So, as if the magnetization at the boundary is acting like an external drive, but this may not be so, because if you have constant density gradient and external drive, the density, I mean if you do not have a density gradient but an external drive only induce a current, but not any non-trivial density profile. But here we see that the density profile is first of all there is a existing a density gradient in the bulk, and also a non-monotonicity near the boundaries. So, yeah, so this we cannot really think of this magnetization as an effective drive. So, now you increase the density gradient. So, what will happen? So, say this P0 is now increased on this right reservoir. So, it will induce a current against the magnetization driven current, and at some point the current will be 0. Now, this is interesting at least to us, because you imagine a picture where you have a fixed wall, two walls, so that there is no particle current, but somehow you have some mechanism in which you give to different magnetization at the two walls, and that different magnetization will create a density gradient. It is very much like Seebeck effect, where you give to different temperature at two walls and a density gradient is created. But again it cannot be exactly Seebeck effect, because this Q0 and Q1 we do not see any associated different flux, because there is also heat flux, but here we do not know. But somehow the similarity is achieved where these Q's, here they act like temperatures, here they act like some kind of external force. And another consequence is, in this case, the density profile is actually constant in the bulk and the magnetization is almost 0. So, unlike the passive system where the density gradient gives the density profile, here the current that controls the density profile more. And this is the summary of this case. So, this is the steady state result of the boundary driven process. Now, we want to look at the time dependent behavior. So, for the time dependent behavior, we have to solve the entire master equation. This is the linear operator with the boundary condition. So, the general solution is you just write the steady state and you have this spectrum lambda and an eigenfunction. So, if you can solve for L, you have this general solution for all times, and from the initial condition you can get Cn. So, it is the standard procedure. However, it is usually not very easy to go through the procedure and solve for the spectrum. Here it turns out that this time dependent part, it actually solves a both side absorbing boundary problem. So, the problem just reduces to an initial value problem with absorbing boundaries at both ends, and now this is solvable. So, it turns out that there is a symmetry. The symmetry, it is like a reflection symmetry. So, a particle starting here with spin this way and a particle starting here with spin that way, these two are equivalent. So, you can use this symmetry and you can analytically solve for the spectrum, and it turns out that the spectrum is distributed in two bands. One is near 0, lambda equal to 0, yeah, okay, and this is very much passive like you see, and another band which is near 2 omega, omega is a tumble rate, and we want to look at the last time behavior in which this 2 omega band just vanishes. At large times this will be almost 0 and this will contribute. So, now we are actually looking what is the active contribution to the dynamics and all, but we see that it is very much passive like here also. So, we go at the next order and we see that this active contribution proportional to V, it comes of order 1 over L. So, now this is the relaxation for n equal to 1, this gives a relaxation behavior, and there is a non-monotonicity because at small system size the tumble rate governs the relaxation, but when the system size is large you have many tumbles, so you go to diffusive. So, but when you calculate the eigenfunction, so this is clumsy, you need not look at that, but the point is in the eigenfunction also the leading behavior is passive like and the active contribution is in the subleading order. So, apparently active contribution occurs as corrections, and if you solve for the entire spectrum you write it as a sum and you see that this active part is of the order 1 over L. However, we find that there is a n multiplied. So, at very large times you only have 1 or 2 n's contributing, but for a large system you have an intermediate time scale where you have not relaxed, but your initial 2 omega band is relaxed. So, there is some intermediate regime. So, what is happening there? So, in that regime you assume the system to be a semi infinite system, and this problem can be analytically you can actually find the spectrum, and it turns out that if you calculate this active, you sum over all the terms, you call this active term, you know the passive contribution and you take the ratio, call it R, and it turns out that in this intermediate regime, intermediate large time regime, this R that can be very large. So, actually although individual terms they contribute in a small amount, when they add up they can actually exceed the passive behavior and they can actually determine the behavior of the system. Even in the bulk, this is extends to infinity. So, in the bulk we never expect that. So, when you go far from the boundary, so there is no boundary effect, it makes a lot of tumbles, and generally there is no active kind of behavior remains and it is effectively passive. But at least in this case we find it is not so. And this is how the distribution looks like, and it agrees well with the data. So this is the characterization part is mostly complete from our side, but we have one interesting observation. So we just show you the distribution, so you need not follow everything here. So it has three components. One is this passive component, which is usual, and then there is this red one, which is the new active component that gives me this active contribution, and then there is this exponentially decaying terms, which is the boundary layer. So the boundary layer is even present in the time dependent problem also. And again you see that this term in the square bracket, this is the Milnor length, and this is just to show that the diffusivity has a non-trivial consequence. When D is 0, no thermal noise, the total balance is retained of the different kind of particles, but when you switch on a thermal noise, then the particle demography changes and the net magnetization is induced in the system, which is not there earlier. And you can combine this part to in a more rational form. This is passive like, but there is this important new contributions which gives rise to important effects that we have just seen. And it turns out that here if you put x equal to minus lm, it is 0. So you are, when you are far from the boundary, you see the effective absorbing condition at instead of 0 at minus lm. So this is the significance of Milnor length. So it appears in this problem and it appears even in the steady state. We are trying to understand why. And it turns out that this particular form of distribution is not only true for RTP, but also in underdamped motion for AOUP, and we have some simulation result which shows that even for ABP, this particular formula distribution is there. So apparently we are thinking that there might be a sort of universality in this absorbing boundary problem when it is driven by current noise. We don't have any general proof for that, so we are working on it, and this is what I have to say. Thank you.